something like that. Only Microsoft and the security researcher knew about it. For this talk, I'll be concentrating on CV 2011-1966. And if you go back and look at the advisory for this, it tells you that it was a remote code execution vulnerability in when handling NAPTR DNS records. Okay. Does anyone know what an NAPTR record is? Neither did I when I looked at this thing. So we all know what a DNS server is. We give it a domain, it will give you the IP addresses. So these are all records which are stored in your DNS server. And NAPTR is just a type of a record. At this point of talk, what we want to know is it's just another type of record which is stored in your DNS server. We don't care much about what the NAPTR record is. And as I told you that what we'll be doing is we'll be taking security patches and we'll be trying to reverse engineer them. So the tools that I use is IDA Pro and TurboDiff. Everyone knows what IDA Pro is. It's a disassembler. You give it a binary, it will give you the code flow and things like that. It will give you a lot of details about that binary. And TurboDiff is just a plugin for IDA Pro. What it does is we do diffing every day in our daily day-to-day tasks. What TurboDiff does is it does not compare. It will compare two binary files rather than two text files. It will give you a difference between the two binary files. Just to give you guys how TurboDiff and IDA Pro looks like, this is what you see when you open a binary in IDA Pro. It will give you a disassembly of the code. It will show you the flow graph of the binary. There are these tabs over here. If you could see, exports are the functions that are exported by that binary. Imports are the functions that are imported by the binary. The strings tabs will tell you what strings are in that binary and things like that. And if you want to compare two files, what you do is you go to edit, go to plugins. There is a plugin named TurboDiff, and you ask TurboDiff to compare it with another file, just so it will compare two binary files. That's it. And once it does the comparison, TurboDiff gives you something like this. It will tell you what functions were identical in in these two binary files, what functions were suspicious. If you see over here, it classifies them as suspicious, some as suspicious plus, and it will also classify them as changed, which is not shown in here. It changed and unmatched. So how the TurboDiff has this some guidelines as to how it tells you the degree of change in the two binary files. And how I look at it is, if the function is classified as suspicious plus, that means the number of changes made by this in these two binary files were very less. If it is suspicious plus, the changes made were more. If it is marked as change, that means a considerable of changes were made. And if it is unmatched, then it's like a totally new function was added to this new binary file. Now, as I told you, we'll be going into some binary diffing and things like that. So I wanted to go over really some very basics so that everyone is on the same page. And this is signed magnitude representation. Now we know all the integers are classified as signed and unsigned integers. So one of the ways of representing an integer is using signed magnitude representation. It's really very simple. What you do is take an integer, convert it into a binary number, and the MSB will tell you if the integer is positive, if it's signed integer or it's an unsigned integer. I mean, if it is if the MSB is 0, that means the integer is positive, and if the MSB is 1, that means the integer is negative. So if for 1 byte, it could represent from -127 to +127. Okay, and because we'll be doing some assembly reversing binaries, we need to know some assembly. But trust me, this is really simple assembly. Don't get scared. It's really, really simple. We just need to go over like 2 or 3 assembly instructions. So the first instruction is move instruction. Very simple. The syntax is move destination comma source, and what it does is whatever is in the source is moved to destination. Example is move AX comma BX, and this instruction would do is whatever is in BX would move to AX. Okay. The only important thing we want to know about move instruction is that the source and destination has to be of the same size. So if the source register is 16-bit, this has to be 16-bit. If the source register is 32-bit, this has to be 32-bit. Any questions still here? But often what happens is, we know that when two integers are added, it's a high probability that the result would be a value that cannot be stored in just like when two 16-bit integers are added, it's a high chance that the addition will the result will exceed like the destination will not 16-bit destination will not be enough, and we need a bigger space. So for that, assembly gives us two instructions. The first instruction is move_sx. It stands for move signed extended, and per the definition it fills the MSB of the destination with source operand signed bit. Kinda confusing over here, but a picture will make it more clear. So what we are doing in this case is we are trying to move an 8-bit value to a 16-bit destination. So what happens is the least significant bytes are copied as it is, and the MSB of the destination is filled with the source operand's byte. So in this case, it would be filled with 11111111. Okay? Questions? No. The second instruction is move_zx, and it stands for move 0 extended, and per the definition, it fills the destination with MSB of the destinations with zeros. So picture will make it more clear. Again, in this case, we are trying to move an 8-bit value to a 16-bit register. And what happens is least significant bytes are copied as it is, and the MSB is filled with 0000. Okay. Let's try and see move_sx and move_zx side by side, and I think this will make things more clear. So our example is move_sx EAX, 128. Now 128 is represented as 10000000. What happens is least significant bytes are copied as it is, and because EAX is a 32-bit register, what happens is the top 3 bytes are filled with 11111111, and once this instruction is executed, EAX will have something like this: FFF, 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 and 80. Questions? No?
So it depends on register size, how many get zeroed out.
Yeah. So if it is just move_sx EAX, not EAX, just EAX, then only first only
Like the upper.
yeah, just the upper part will be filled. The MSBs will be filled with with the source operand signed bit. For move_zx, what happens is again 128 10000000. Least significant bytes are copied as it is, but the top 3 MSB bytes are filled with 000, and after this instruction is executed, EAX equal to 000080. Only this much is the assembly what we want to know for this talk. Okay, so let's move on to our example of MS11058. And if you compare, TurboDiff tells you that most of the functions are identical, and it lists 4 functions as suspicious and suspicious plus plus. Let's see what these functions are. The first function is remote choose send. The second function is remote set valid response, NAPTR wire read, and remote build vlist from new zone. So remember, we are trying to analyze a vulnerability with NAPTR records. TurboDiff tells us that there are these 4 functions which Microsoft changed with this patch. So if you guys were to pick one function which you will try to reverse engineer first, which function would you pick from here? Sorry? Yeah, so that's a correct guess, right? So we know that the vulnerability that we are trying to fix is related to NAPTR record. TurboDiff tells you that there is a function named NAPTR wire read that has been changed by this function, by this patch. So it's our obvious guess that the function which we'll choose is NAPTR wire read. So
doesn't that just also tell you if anything after that address was changed too?
After
so
that
address, if the offset of the function was changed.
So TurboDiff lists all the functions that were in that binary.
Okay. Oh,
Okay.
I see. It doesn't.
Yeah. So
it
does.
show the ones that moved.
Yeah. So if you see, most of them were identical. Only 4 functions were changed by this patch, and of them, yeah, NAPTR. So at this point, we have done our first step, where we try to see what was the change made by the patch. Now let's move on to our second step, where we'll what we'll do is we'll try to analyze what the change was made by the patch. So this is how turbodiff tells you what changes were made to that function. On the left hand side you see is the unpatched function, and the right hand side is the patched version of the function. And if you start comparing each instruction one by one, you will see that there was only 1 byte of change that was made by this patch. So to fix this vulnerability, there was just 1 byte of change made by Microsoft to fix this patch. Okay, let's try to see what's going on in this thing, with this thing. So we all know that this patch, what it did is the unpatched version, it was MoveSX, and the patched version had MoveZX. So MoveSX was replaced with MoveZX. Okay, let's try to see what's going on in this bunch of assembly instruction. So what happens over here is MoveSX EDI byte pointer EBX. What this instruction does is a 1 byte value was moved to a EDI with MoveSX. So if I were to replace this in a very simple language, what I could do is I will tell X is moved to Y. Okay. The first instruction moves 1 byte value to EDI. Whatever that byte value was incremented by 1, EDI plus 1, and that value, the resultant value, is loaded in EAX. So if I were to replace this with very simple instruction, I would say X is moved to Y, Y was incremented by 1, and that value is moved to Z. Now you see there is this push instruction, push instruction, push instruction, and there is a call to memcopy function. So what this bunch of this 4 lines of assembly function is doing is, it's just a simple calling memcopy with destination scores, comma Z. This is what it is trying to do over here. Okay. Any questions till this point? Okay. So based on our previous example, what would happen if I was, this value X is set to 128 based on the example which we have seen before? Can someone tell me what will be the value of Z after that?
129.
No, that would be 129 if there was just a move instruction, but this is move SX.
Much higher than 129.
Yeah, so what will happen is the top three bytes will be filled with 11111, and what will happen is the resultant value would be FFF, FFF, FFF 81.
Something around that.
Yeah, okay. So if you were to convert this number into decimal, this is approximately equal to 4 gigabytes. Okay. So what was happening in the unpatched function is there was a memcopy function which was ideally trying to copy like 4 gigabytes of value. If you were to put this number to be 128, it was trying to copy 4 gigabytes of value. But in the patched version, what would happen is it would be 00000081. So in the patched version, it was only trying to copy 129 bytes, and in the unpatched version, it was trying to copy like 4 gigabytes of value. So what would happen if the destination buffer over here is not equal to 4 gigabytes? Obviously, that would lead to a buffer overflow, and it's a very high probability. I can tell it with certainty that there would be no developer who would try to write a memcopy, who would try to code like with a memcopy function, and he's trying to copy like the 4 gigabytes of value. 4 gigabytes is like the maximum possible address space that a 32-bit CPU could address. So it's a high chance that you would get a crash if you put this value to be 128 in here. So how do I exploit this thing?
Why did they use a full register for that?
Sorry?
Why did they use a full register for that, right? If they couldn't ever have an actual need for 4 gigabytes, right? They could never have an actual need for more than a 2 byte.
But they did it, right? Yeah, it happens. So how do I exploit this? Turns out it's not very difficult. What we have to do is we have to somehow put this magic number 128 somewhere in this thing, hoping that it would crash the target. I will exploit the vulnerability. So at this point, what we have done is we are completed with our second step where we wanted to analyze what was going on with the patch. So now let's move on to a third step where we want to write proof of concept for this exploit. And for that, this is how a sample NAPTR record looks like. Okay, what you do is you register a domain, and there are these fields in here: order, preferences, flag string, service string, replace, regular expression string, replacement domain, and things like that. Turns out if you want to exploit this vulnerability, you don't have to be an expert with NAPTR records. And for the matter of fact, even at this point, I don't know much about NAPTR records. So all I care is, there is somehow I want to put this magic number 128 in one of these fields, hoping that it would exploit the vulnerability. So what I do is I start putting 128 in here, in this string, but nothing happened. Can someone give me a better solution of what should I have done rather than just putting 128 in this thing?
You just put something that's 128 bytes.
That's correct. So what I do is, rather than putting, like what I did is I start putting 128 in all these fields and do an NS lookup, but nothing happened. So what I did is that I saw there was this field named regular expression string, and it was accepting a lot of characters. So what I did is, rather than putting 128 in here, what I did is I started putting random characters in here, and at the point when I reached like 128 random characters, when I started inserting 128 characters in here, and when I did an NS lookup on this thing, and the DNS server went down. So yeah, at this point, so yeah, this is how I created a proof of concept for this, and how a typical attack scenario would look like for MS-11058. So what an attacker could do is, he could register a domain with a malicious NAPTR record, and if he was supposed to target a company named XYZ, what he could do is, he could send an email to one of the employees of this company with a link, and when this guy tries to open that link, it will send a request to the DNS server of this company to try and fetch a record for that domain. Now, when this DNS server tries to fetch the record for that domain, this malicious record would come in here, and this DNS server would try to parse that record. And when this DNS server tries to parse this record, this DNS server would crash. Okay. Any questions on MS-11058? Okay. So what we want to know about this thing is, when this DNS server tries to parse this record, only the DNS server component running on that server would crash. There won't be an entire blue screen of death on the target, because DNS server for the Windows, it is not a kernel component, but it's sort of in the application layer. So only the DNS service running on the server would crash, there won't be any blue screen of death on that target. So let's try to do something more malicious, and this brings us to our second example of the talk of MS-11077. MS-11077 was released last year in October 2011, and what it did is, it fixed 4 vulnerabilities in Windows kernel. And for this talk, we'll be concentrating on CV 2011-1985. And if you go back to the advisory, again it tells you it's an elevation of privilege vulnerability because of insanitized input. Again, not giving a lot of information as to what this input was, how it got fixed, and things like that. So our first step to do binary diffing for this patch, and it tells you in this case that there are some functions were identical, but there was this whole bunch of functions that looked suspicious, suspicious plus plus, or changed. Can anyone tell me why for the MS-11058 example there was just like this 4 functions were changed, but for this example there are like this many functions were changed? Can anyone tell me why is that the case?
It was a larger change.
Sorry?
It was a larger change.
That's exactly correct. So we know that for MS-11058 there was only 2 vulnerabilities were fixed by the patch. But with this MS-11077, Microsoft bundled this patch to fix 4 vulnerabilities. So obviously, because the number of vulnerabilities fixed by this one patch is more, the number of changes were more. So what I do is I start looking at each functions one by one. And what particularly struck me at this point was there were 3 functions. They all start with NT-user fn, NT-user fn, NT-user fn. All these 3 functions, they had the similar code changes. So whatever was the code change made to one function, that was ideally copy pasted between all these 3 functions. So I took one of the function name NT-user fn NL box string and I start to analyze it further. Can everyone see this thing? Because many times there are like these conferences and people are not able to see this. So NT-user NL box string. On the left hand side is the unpatched version, on the right hand side is the patched version. And I start, if compare each instruction one by one, what you would see is there was this one additional instruction added over here. It was not in here. And there was this whole block of code that was added by this function, okay, by this patch. So let's try to analyze what this patched version is trying to do. Okay, so we know that there was a additional instruction compare ECX FFF 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 FFF. This is nothing but 2's complement of -1. So what it is trying to do is it is trying to compare the value of ECX with -1. Let's see. Before this instruction, there is a move instruction, move ECX EBP plus arg of 0. This is nothing but whatever is the first argument passed to this function that was moved to ECX. ECX is now compared with -1, and if it is found to be -1, what it does is it calls a function named set user last error with this value, and it bails out of the function. So let's try to analyze what's going on in here. The first argument of this function is compared with -1, and if it is found to be -1, it is returned. And then I did a bit of a googling as to what this thing is, what the set user last error is with this value. So it turns out this is in system error code for Windows invalid handle, error invalid handle. So let's try to see what's going on in here. So in the unpatched version of the file, what was happening is whatever was the first argument passed to this function, it did not care about it. Whatever it was, it took that thing and started processing it. But in the patched version, what is happening is the patched version is explicitly looking for the first argument passed to this function. It is checking that if it is -1, if it is found to be -1, it is not happy, it sets an error and it bails out. So how would you exploit this thing? Sorry?
Try to pass the value of -1?
Yeah, that's correct, right? Because we know that in the unpatched version, whatever was the input, function was happy and it started processing it. And in the second thing, in the patched version, what it is doing, it is taking this first argument, it is checking if it is -1. If it is found to be -1, it is not happy and it bails out. So if you were to exploit this thing, what you do is you set that first value to be -1, and there was a little subtle hint in that new block of code. It told you before bailing out, what it did is it told you that okay, this is an invalid window handle. So that what that means is that the argument is of type handle, right? That's the reason it is telling you that it is an invalid handle. That's a very subtle hint, but we don't need that to exploit this thing. So let's see a proof of concept for MS-11 077. Just really simple, just 2 lines of code, and you have a blue screen of that on the server.
Just hard code the handle.
Sorry?
You can just hard code the handle.
Yeah, it's not like when you try to compile, if you don't put this handle over here, what it will tell you that when compiling it will give you a warning, but it still execute. So yeah, this is as simple as this. So yeah, this is the proof of concept for MS-11 077. And what I want to highlight at this point in talk is that this reversing patches technique is really helpful for penetration testing guys. What they can do is they are just now not limited to the exploits available from the exploit packs, but what they could do is they could actually do the reverse engineering of these patches. They could do this binary diffing, and they could just create their own exploits rather than relying just on the exploits available from the commercial packs. But it is better that they start creating their own exploits, right? So it turns out this technique is good for the penetration testers, but there are this bunch of guys who are already using it. Can anyone guess who are the ones who are using this the most? Sorry? Malware authors. So these patches are released, malware authors, what they do is they start doing this binary diffing, and they try to come up with exploits. They try to come up with the custom malwares to exploit these vulnerabilities. And for that, I'll show you an example of a third example of MS-12004. It was released in January 2012, and it fixed 2 critical vulnerabilities in Windows. And for this talk, we'll be concentrating on CV 2012-003. If you look at the advisory, it tells you it's a remote code execution vulnerability when trying to parse MIDI files. Does everyone know what MIDI file is? These are like really small music files. Seems to be very harmless. But the nature of this vulnerability that made it more lucrative for the malware authors is, first of all, it was a remote code execution vulnerability, and these files look very, very harmless. So if I send you an email saying, hey, could you listen to one of the music that I've composed, and you click on that link, your browser would try to parse this file. And if this is a malicious file, by the time you just click and it is trying to parse it, you are basically owned by that time. So this nature of this vulnerability was very lucrative for the malware authors. Okay. So this is the result of TurboDiff. It tells you that this patch changed just one function. All the functions were identical, but there was this one change. There was this one function change. The function name is MIDI output poly event, and let's try to analyze what was going on with this thing. So on the left hand side is the unpatched version, right hand side is the patched version. And again, if you start comparing instructions one by one, there was this one instruction that was added in here, and BL, 7FH. So what this patch was trying to do is, it was trying to take one of the variables, and it was doing a logical AND with 7FH. When you do a logical AND with 7FH, or what happens is, if this value is greater than 7FH, what it does, it tries to limit that variable. So if the value is greater than 7FH, it would be reduced to 7FH. If it is less than 7FH, it would keep it as it is. Okay. So very simple change. What it did is, it was trying to check a variable and it does not want it to be greater than 7FH. So how would you exploit this thing? Sorry? Yeah, that's true, right? Because in the unpatched version, it was happy whatever the value is, it's not doing anything. But in the patched version, what it is trying to do is, it is checking that one variable, and if it does not want it to be greater than 7FH. So if you were to exploit this vulnerability, just put that value to be greater than 7FH, right? And turns out, if you are good with the MIDI file formats, that variable that it was trying to check is the note number parameter, and if you put this variable to be greater than 7FH, it would crash crash the application. Sorry?
Because there's no handler for
yeah. So I cannot show you a proof of concept for this thing because it's a MIDI file, but I'll be putting it on my blog post, and you guys can download it from there if you want, and proof of concept exploit. Yes. This patch was released on 10th of January 2012. Can anyone guess when was the first time a malware found in the wild exploiting this vulnerability?
The 11th.
So for malware authors, they just don't want your application to crash. For them, it is more, what they want is, they want to get reliable code execution. So you can create a proof of concept which would give you a crash on the target, but if you want a reliable code execution, you need to put in more efforts. So turns out the first time the malware was found in the wild exploiting this vulnerability was on 26th of January 2012. So just like 16 days after the patch was released, there was a malware in the wild exploiting this vulnerability. Just imagine, like previously no one knew about this thing, but at the time, like once Microsoft released this patch, there was already in 16 days, there was a malware in the wild exploiting this vulnerability. So what we have seen is this technique is useful for malware for penetration testers, malware authors are already using this. How could a vulnerability researcher, if you are finding new vulnerabilities, how could you use this technique? Turns out the hard truth is patches are not always done right. These patches are supposed to fix some vulnerabilities in your system, but often what they do is they introduce new vulnerabilities. A very good example of this is PHP 5.3.9. It was released in January 2012, and one of the things that it did was it fixed the hash collision denial of service vulnerability. So what hash collision denial of service vulnerability is, you have a web server, what you do is you just bombard that web server with lots of post variables. Now these post variables, when they reach the web server, they are stored in a hash table. So what you do is you bombard that web server with lots of post variables, and when these post variables go into the hash tables, because you send a lot of post variables, like there is a high chance that there would be a hash collisions in them, and when the hash collisions occur, what happens is the web server will consume a lot of web server resources and basically causing a denial of service vulnerability on that target on the web server. It was a very popular vulnerability, and it did not just affected PHP, but all the web servers with Tomcat, ASP.NET, everyone was affected. Microsoft fixed this vulnerability with, I believe, MS 11.100. And how PHP fixed this vulnerability was, it introduced a directive named max input wheres. So what this directive could do is, it will allow a web server administrator to set a limit to the number of post variables it is willing to accept. So the less the number of variables being sent, lesser are the chances that there would be hash collisions, and lesser is the chance that you will have a denial of service vulnerability. Let's look at the patch for this. Very simple change. If you see over here, what it did is it was trying to put a limit that it will only process those variables that are less than that set by the max input wheres. It was so good so far, but what they did not do is, what if the number of variables, if an attacker is still trying to send a lot of variables, what to do with them? So rather than an else condition over here where it should have ideally returned from the code, what happened is the code was allowed to execute, and what this thing did is, they fixed the denial of service vulnerability but introduced a remote code execution vulnerability. So just imagine a web server running a PHP with a remote code execution vulnerability. So what the vulnerability was, vulnerability occurred when the number of variables exceeded max input wheres. The variable is of type array, and instead of an else condition where they should have returned from the code was allowed to execute, and it introduced a remote code execution vulnerability. Proof of concept for this thing, very simple. What you do is just do a post on the target web server with random variables. 1000 was the default limit set by max input wheres, and you just add an array element over here, and you have a proof of concept for remote code execution vulnerability on PHP 5.3.9. Summary. So as I mentioned in the starting that we'll be reverse engineering 4 security patches. We did that. We exploited all these vulnerabilities. It's a very good technique for penetration testers. They are just not limited to the exploit available from commercial packs, but they could start writing their own exploits. Vulnerability researchers, it's a very good technique. We could just find new vulnerabilities based on reversing these patches. And for IT administrators and for people like us, we need to start updating our systems as soon as possible, because there are people out there who are trying to exploit this vulnerability the day the patches are out. So we need to be on our toes. That said, I think I don't have time for questions and answers, but you could always send me questions on. We pushed you back. Yeah, we pushed you back. Oh, okay. Yeah, any questions and questions, I'll be more than happy to answer them. I had to run through the last.
Are you going to be here after this for people who might want to ask you questions?
Yeah, I am. Yeah. Okay. So if you have any questions, just ping me. All right. Thank you.